Hey here, Paul from Evoke Polymers. Today, I'm bringing on a special guest to talk about a really cool subject. I'm super excited to have him on here. As you know, we work with all of our customers and our community of designers and engineers to talk about the importance of sustainability, cost performance benefits, and all the other small nooks and crannies that go along with getting a high performance injection molded part. Now, wall thickness uniformity being one, material selection being another, cavitation being another. We obviously have the polyestimator to help us with some of those things. But one of the things that kind of came across my bow not so long ago was the idea of fluid injection molding. And so I, after being in the industry for, injection molding industry for many decades, don't know a lot about it. And I think there's a lot of people in our audience that have the same questions. So we brought Oliver here to talk a little bit about fluid injection molding. And so this is a technology, as I understand, what's quite a bit different than gas assist molding, which is also very cool. So with that being said, I'd like to introduce you to Oliver. Oliver?
Hi, thank you for having me.
Yeah.
My name is Oliver Stahl. I'm with Chemigon. We are a distribution and technology consultants company. We operate out of Akron, Ohio, but manage pretty much the entire North American region. Subjects such as fluid injection are our specialty, and I'm happy to be here to talk about it.
Excellent, thanks.
So, if we want to go through it case by case or subject by subject, we can start with a general explanation how the technology works. And I can kick off by saying it is a conventional injection molding process. We fill a cavity like we do with any other thermoplast. The only difference, and the main difference, is we then, after the completion of the shot, come from the opposite side and shoot a water jet through the tool to move the molten core back into the injection molding machine. And that is the big difference to a normal process, and also a difference to gas assist.
And I think that's one of the things that really just struck me as just awe-awakening, was that there's all these technologies to make a plastic part. There's roto-molding, there's blow molding, there's injection molding. But with this technology, you're going to get all the precision of injection molded part, but you're actually going to use water and hydraulic pressure to drive that molten liquid through the cycle back up into the screw of the machine.
That is correct. And the specialty here is you do not go into an overspill cavity. This is what we know from gas assist, a great technology, and applicable to a lot of applications. But fluid injection has two major advantages. One is you bring the product back into the injection molding machine, that it is ready for the next shot. And the second one is, because the fluid is in the tool, you have an internal cooling process. So not only do you cool conventionally like we all know, now I have a fluid inside that came in at room temperature and is now heating up, takes the energy from the polymer that builds the part, and we evacuate the water thereafter and are ready for the next shot. The water stays in the system and is in a closed loop, ready to go for the next shot.
Yeah, and so I've got like an example of a part here that I haven't really talked to you about, and I wanted to show you a little bit. But a traditional off-the-shelf component that has a gas assist is going to shoot and mold the part, and then they're going to come back with a gas assist, fill that cavity, and push out any excess that gets sent back to the machine or gets discarded as waste. But what you're doing is you're going to shoot the liquid into the end of the part and drive that extra liquid all the way back up into
That is correct.
the screw.
That is correct. And because the product, the water is non-compressible compared to gas,
right,
you can define the flow of water exactly to the position where you want to have it. You'd never run the risk that the water gets into the gate or, God forbid, into a barrel. This water would go only to the end of the tool in the cavity, to the place you want to have it, 100,000 times exactly to the same position.
And so, as we know, gas is compressible, liquid is not. And when
Exactly.
you've got that hydraulic pressure driving that liquid through the part, where gas is going to expand and you're going to have a lot of variability. But I think one of the most, incredible aspects of this technology would probably be the thermal transfer, right? Like actually getting water on the inside of that part and cooling
Yes.
that part as fast as possible. And so we're going to talk a little bit about some examples. I'll ask you to kind of tell us how the technology works a little bit. We'll go through some sample parts, what we're seeing in cycle time reduction, which probably doesn't even affect, cycle time reduction, equates to better cost, less energy, less electricity, better for the environment, a lot of call it feedback or benefits on a carbon or just on a structure from an environmental standpoint. And so with that being said, is you're also reclaiming that material right in the screw per shot, which is another big benefit as well.
That is correct. If we take a look at the drawing here and see the process, how it works, in picture 1, you see an empty tool. It is a door handle, and for simplification, this is just a random application. It could be anything you can think of. The green material sits in the barrel. The screw is about to move the material forward, and you see then on the second upper right picture that the cavity is completely filled. My screw moved forward. I'm done. That is what we know. Now, with picture 3, bottom right, left, you see that we come from the opposite side and we shoot water with pressure into the cavity. And you can see then that the screw travels back, makes room. And how does that work? The equipment of the water injection unit speaks to the press. Certainly, we need a certain communication. And this interface we use is a Euromap interface that lets the two units communicate to each other. And by the way, that works with pretty much all established presses.
Sure.
You can
So
buy.
it's universal. You can run it
Yes.
on a 610-ton press,
Absolutely.
a 300-ton, 60-ton press, which is really nice to know. But now we're coming in at the gate with the flow of polymer, and we're coming opposite of the gate with the water.
That is correct.
Okay.
And we will see on a later slide how that works in specific. So let's move forward and talk a bit about the technology. So first of all, you would be able to utilize pretty much every polymer. However, in our world, 9 out of 10 times we either use a nylon 6 or 6/6 or a polypropylene. In all honesty, that makes about 90% of our applications,
Okay.
I would say. That can be a glass-filled material, that can be carbon fiber, it can be long fiber or short fiber. So you're pretty flexible. We even have certain products that have strength by having cosmetic appealing surfaces outside or inside. Let's say we think about a part that should look good from the outside. I need a nice outer surface. I would probably take a gas assist grade. That would give me certain advantages. If I have a tube for fluid handling, for instance, my inner surface matters more. Therefore, certain compounders developed fluid injection modified materials that you can use. So we're pretty flexible on the material selection.
Is talc also another additive that might be an option to work? Okay.
Absolutely.
Excellent.
Absolutely. This is a mineral or talc-filled product.
Oh, it is? Okay,
Yeah,
cool.
absolutely.
Well, maybe that's a good segue into getting into some examples. Huh?
Yeah. I mean, one aspect we could probably show quickly would be the process variant of a application that uses just water. Or quickly, if you want to define your wall thickness, you could also modify it by using a projectile. So in other words, not only do you shoot the water through the tool, in front of the water is a little bullet that makes exactly that much room that you define the exact wall thickness. And that means we can show you pretty much both options, whereas structurally sound products like, for instance, a clutch paddle, of which we see an example later on, you need a certain wall thickness. This is of interest. You want to have a stiff part. On the other hand, you have probably certain thinner applications for fluid handling where 2-3 millimeter is fully sufficient.
Mhm.
In this case, you can shoot a bullet, and maybe if we take a look at it, there is an animation, and if we let it run quickly, you can see that the material flies into the cavity, and here you see from the opposite side, not just the water, but especially a little projectile shoots through the part. Not to go too much into detail, but you see that you can clearly define the wall stock by using the bullet. But from there, probably to more general topics, we can define the design with the help on the one end of the experience of our people at PME, but on the other end, Moldex is one of the simulation companies that helps us greatly, and that would be a partner. So
Absolutely, yeah.
Quite often the question arises, can we simulate what we do here? And the answer is yes, simulation of the process is possible.
Oh, very fine. So when you talk about projectiles, just so we're clear, the projectile is used when you want perfect uniform wall thickness.
That is correct.
Okay.
That is correct. And the nice thing talking about sustainability, but also about quality control, you use the bullet made of the exact same polymer as the part, so that you can shoot the bullet and you don't have to take the bullet out. The bullet travels to the very end of the part. You cut it off and you throw it into the grinder, and you use the bullet as a regrind for your continuous molding process. Again, no waste.
Right. And so how many, like when you look at a spectrum of different parts and processes and stuff, how many of these processes use bullet versus no bullet? Like what would you guess?
I would say the majority is probably without.
Without bullet, okay.
Yeah.
So a very, very specialized process to get that wall thickness. Because you probably want to get as much wall thickness out of it as possible when you're trying to optimize that part cost, right?
Certain applications require a more solid part. You use the channel not for fluid handling, for instance, but for structural stiffness. And you build a collar around an application. You want to stiffen something. Think about one of the applications that we show, like wheelbarrows or bike frames. Anything we might see on future slides. You need a certain wall thickness. To go too thin is counterproductive. So with that, I think
it's application dependent. Is
absolutely.
What it is. Yeah,
absolutely.
Okay.
Absolutely. So just to give a quick idea about the size, so that what we see here on the picture is about the size of the equipment, and you can perfectly hide that behind an injection molding machine. It's nothing that is so big. It is mobile. You don't want to move it daily, but if you have a project on press A and one in 3 months at press B, to move the equipment to a different location is comparably easy. And the terminal you see there, that sits next to the injection molding machine. So the operator has always direct access to the platform and can manipulate the process if necessary.
I mean, what I love about it is that it's mobile. Like I can run it on different molds, different presses. I can bring it around. And so after you've made the commitment to go to, fluid injection molding, you've got a whole plethora of things that you could use.
That is very,
right?
that's very true.
Nice.
Yes. So going into applications, the typical beginning was fluid handling. A tube is almost an obvious application at the beginning. You think immediately about it, but then from there we branched out to other parts. But let's stay with the tube for a second, because
I think this is a great one to start talking about.
This is an interesting one indeed. If we take a look at it, you see a regular tubing structure, but some flexible components to it. And the way you do it is you injection mold, you fill the cavity, you send a water channel through it. That is my step. But now I take down the pressure so that I can open a slider. And you see it on the drawing there. So the slider opens, the horizontal slider opens. That has no other design. The vertical slider has these structures designed and built in. So we close again, increase the water pressure. The material is at that stage still semi-molten.
Right.
And I'm able to press it into the design and create this corrugation, and that makes now a super flexible part. You are able to produce a drain channel with molded clips, two flexible components, all in one shot, one material in about 40 seconds.
This is phenomenal. And
this is cost saving.
Well, the thing I love about this is that you're getting injection molded features integrated, okay, at a wall thickness that you could only do with blow molding or maybe roto-molding or some other type of process. So you're getting this really, really nice features. You're packing the part out. You're coming back in and squeezing liquid almost like a jelly bean. I always talk to my customers about the jelly bean effect, is that when that liquid plastic goes into the mold, as it cools, it's cooling from the outside in. The inside is like a soft jelly bean. The outside is hard. You're squeezing the inside of that jelly bean back into the screw of the press itself. So yeah, fantastic.
So that was the beginning, but what we see today actually is more a move towards structurally sound products, and the wheelbarrow might apply to many applications. It's actually as trivial as it sounds as a part. It is very interesting in terms of structural stiffness, length of an application. Think about this goes over the entire length of 85 inches, a completely hollow structure. And here, see the channel, which is
so we've got a wheelbarrow
massive.
Handle is what you got there.
That is the handle. This is the end of it, right? And here I can hold it, and it's a super stiff application. And we make an entire wheelbarrow in 1 minute. Oh
my God, that's
when
amazing.
You think about the cost of that part, the surface is really decent, and the efficiency is high. It's a glass-filled polypropylene, so also material cost is very reasonable. And this is just an example. I mean, this is one application. Think about any other kind of structural application. This could go into the furniture industry.
Yeah.
This could be a covering of a collar that goes around a battery tray for an e-vehicle. There are a million applications.
So there's automotive industry, there's consumer products, recreational. There's a lot of different applications for this. And what I really love is to be able to pack that part out, get that beautiful surface finish with all the textures that we love, and then to be able to optimize it by pulling that core out and pulling that liquid out of that part.
Yeah, and you would find its way also into sporting goods, for instance. We can before we look into this, let us check a little bit the functionality here. If we go with that animation, you see really how the process works. So our
this is really helpful, by the way. I really like this. This
I hope so. Yeah, you see the filling of the wheelbarrow design here. So the screws traveling forward, we fill the part entirely. Now we give it a second that the product can freeze.
Giving it a little jelly bean coating.
Now we have the jelly bean effect, exactly. And now we fill top down. Now we shoot the fluid from the bottom up, and we move the material, the molten core, back into the press, and you see how the screw is traveling backwards. So my material is back into the injection molding machine, and now it is hot. The water took on the temperature, and now it has the tendency to convert to steam. That is what it wants to do, right?
And that's the question I think everybody's wondering is, where does the water go?
How do I evacuate it? Exactly. So water sits in there under high pressure. We do not allow it to convert to steam, but as soon as we open the valve and make a little room, the hot water wants to convert to steam. Steam means pressures. Pressure means evacuation.
Wow.
So water's gone. So it's pretty simple, and you use gravity to evacuate it. So the tool design is usually so that you produce top down, water up, evacuation down. So it's always the same principle.
Fantastic. Now, do we have to worry about the pressure of that water coming out when it's converting to a gas or converting to steam? Do we have to worry about where that's going to be exited and how it's going to be located? And do we have to design that in like a cap to close it if it needs to be watertight?
You have an injector in the tool. That's the only thing you need to do. So to say I modify a gas assist application, for instance, into water is a rather difficult exercise. I would rather go for new applications instead of converting them. But the fluid itself, when it evacuates, is of no danger or doesn't even come out. So
it stays, it's retained.
No one even knows that it's a water injection process if you don't tell anyone. So you neither see steam or water drops on the ground. The water evacuates, goes back into the system, and that system has a water tank. So when the water first gets into the system, it goes through a 10 micron filter. We take the water from your chiller system, that's all. So it's regular water, nothing special, no additives in it, and it goes back in a closed loop. So we have pretty much zero cost for operating, whereas gas assist certainly requires that we buy nitrogen and have consume nitrogen. That's not the case here.
And I think one of the things, like when at Evoke, what we do is we go, hyper vigilant on, we just go kind of crazy on water cooling of our molds to make sure we've got tons of flexibility. And we put zones in certain areas of the tool so that we can get that heat out. We're always fighting heat, right? We're shooting hot plastic in, the mold's getting hot. We got to cool the mold. We want better cycle time. We want that to flash. This changes everything. This is, basically cooling from the inside out. I mean, right?
Yeah.
It's nuts. So tell us a little bit more about some of the other sample parts.
I mean, we see bikes, apparently one of the applications the world is nowadays talking about, right? New mobility and biking became a more popular subject. And this in specific, the Lion bike, is the latest design. And not only that,
so you're molding that entire frame and shooting liquid through the entire thing to optimize that.
Yeah.
Now, is that with a projectile, or is that?
No, that's without.
That's without a projectile.
That's without. You use carbon fiber filled nylon to make the frames. Just talking about the material choice. I mean, what is interesting about that bike frame and the application in general? Let's never forget, we use this to integrate functionality. If you take a closer look to the part, you see that the lighting is integrated. What if you make a cockpit for a bike, an e-bike? What if you integrate your front light into the frame? What if you have a battery integration in the frame? So anything you mold, you can utilize the technology by not only creating channels, but the molding. And that's the beauty of our technology in general of plastics molding, is that we have the design freedom. And I think that is something.
I think it opens up a lot of new opportunities.
Absolutely. Now, this is just leisure. We also have certainly a lot in the automotive sector. We saw so far tubing, very often automotive related. We saw a wheelbarrow. That's one thing we see here, bike frames, but we can also take a look. And before we do that, let's see a filling structure before I move on to the more automotive related parts. But here we can make simulations available. This is just one example which we can show. So you see a filling simulation. Here we go. This kind of support will be given. I think just to mention before we move on to other applications, it's not a technology where you are terribly on your own and have to figure it out. A good part of the daily work we do is really helping with the application.
Working with us intimately to understand what are the benefits, pros, cons. Like even the product that we're looking at together right now, I can't disclose and talk about, but we've got a great application to increase strength based on length and width and that ratio of what we can get out of there. But in any case,
it's important that no one should be afraid to implement it, because there is a great technology transfer. It's never the intention to keep it close to our chest. The idea is really to get it out. If you have the support from our engineering team. You have it once and probably a second tool you can already design yourself, and then you can really take advantage of it. But I would recommend to have a close connection to us at the beginning for the first project. We might be able to recommend the right tool maker. We might be able to give you guidance on we would do it, or maybe not a good candidate.
Not a good candidate.
Not every application is suitable for that. Right?
That's right.
It's not. This is not just advertisement for something that works for everything.
That's right. We don't want the tail to wag the dog.
Exactly.
We don't want to be a slave to the tool.
And there's
we
gas
want to
assist,
use it in the right place.
Yeah, there's gas assist that works as well, and there's blow molding that does a wonderful job. Well, it's not for everything, but
that's right.
Where it fits, good fit. We could talk a little bit about the combination of fluid injection and of a channel together with structural integrity of a part. And that, I think, is something that makes 9 out of 10 applications we developed recently. It's not so much the tubular structure. The fluid handling is certainly something that is almost an obvious thing, as probably a bike frame, in all honesty. But what if we combine the channel structure with a mechanically sound product? Let's take a lift gate. Let's take a door as an example. And I do that, obviously, because we have slides here to show. But just stay with the example of a door where you fill a channel, first of all, with the polymer. You then use this channel as a film gate. You push out of this channel into the flat areas to fill the entire large part. And then as a last step, you come, as always, from the other side, and you push the material in the channel back into the injection molding machine. But the main element here is we do not just build a channel. We use the channel as a material distributor. We go as far as we want and then push it into the flat sections, and we make a larger part. And this has been, at that time, developed with European OEM.
So basically, we're going to fill the cavity, and then we're going to go into stage 2, and we're going to pack that cavity, and we're going to get into all the nooks and crannies.
Yes.
And then we're going to time it, and we're going to shoot our fluid recovery injection molding through there, knowing that that secondary pack is not going to be touched. But we're going to get all those details, and then we're going to optimize that.
Very correct.
Okay.
Exactly. Okay. And then once this is done, you have a fully molded part with really an acceptable surface. If you see the example of the Renault liftgate, we see a picture here. You can go one further, and we take a look at the part. Actually, this is the part that was the first big liftgate that has been molded, and you have a channel that goes around the window and goes down to around the rear lighting down to the latch, and this channel has not only a stabilizing factor. We all have probably seen the full plastic lift gates. There is the one or the other OEM that has it in the market, and that has a lot of flexibility. It is a bit of a flimsy application, and so
strong torsional rigidity.
That is the point. And with this application, you get a lot stronger part. And aside of that, we were able to fill the entire part through the channel and make a wonderful application here. And indeed, this liftgate was the first of its kind, and several others are following as we speak.
Yeah, and I'd say that, one of the biggest questions that I had for you when I first met was, what type of efficiency models can you give us for cycle time reduction? And, we don't have, obviously you don't have a crystal ball or anything, but you've given me plenty of examples where you might have an 80-second cycle time with gas, but with fluid injection molding, you would get that down to 35 seconds. Is that correct?
I would say probably that let's talk about a clutch pedal, which we will see on one of the future pages. That is about 35 seconds. If you take a look at it, that's the size of it. A typical application, a typical part times difficult to carry him to every meeting, but
Mm-hmm.
in case there's really interest to see a live lift gate or this front end part, these are available. We can have them, we can show them, and I would say if I take a look at this clutch pedal, this actually was one of the first mass-produced applications in recent years that got a lot of attention, and
Mm-hmm.
we have right now even this application, this tool in the United States. This was a European development clutch pedal.
Mm-hmm.
Obviously, not very popular in the States, but in Europe it's used. And but for show and tell, we have this tool here. We have overall 2 units that are available for testing. Both are in the greater Detroit area, but if someone would like to dig deeper into the subject and has even ideas to see the process or come with an own tool, I think we can make a lot of things happen.
Yeah, that's fantastic. I mean, my mind goes crazy. There's going to be a lot of questions, Q&A, follow-up, based on application. And I think that users out there can feel free to contact you or myself anytime.
Sure.
But one of the things that I just wanted to touch base on as we close is that, our community of engineers, designers, material specialists, anybody that's in the injection molding industry, we want to make sure that we are transparent, okay, and that we show you a lot of options and ideas to help strengthen innovation and to, kind of suggest that, hey, the power that we have when we're designing and developing a part, it's really our moral responsibility to, try to consider the environment and how much energy it takes to make these things and how we're going to design them and where do we need support ribs. So this is a very, very, targeted approach that I really love. So, thanks for coming on.
Thank you.
Look forward to working with you on future projects. And and that's all we got for today.
Okay. Thank you very much, everyone.
All right. Take care.
Bye-bye.
Welcome to Injection Connection, the ultimate podcast for professionals and enthusiasts in the injection molding industry. Whether you're a product designer, engineer, or simply a curious innovator, this is your go-to destination for success stories, expert insights, and behind-the-scenes secrets that drive the world of plastic part production. Are you ready to elevate your injection molding expertise? This is the Injection Connection, where innovation meets transparency and every part is molded to perfection.